Hello and welcome to the Quanscient Allsolve demo. In this demo we will see how to create a geometry using primitive shapes and Boolean operations. We'll see how to use shared expression and also the use of scripting interface to enhance the user flexibility. We'll start creating a new project. Let's give it a suitable name. In this simulation we'll assume that the fluid flow is incompressible and in steady state. We see that there are three ways of starting a project, of which we'll go with the second one, which is create a geometry. We can see some primitive shapes displayed under this option. For our expansion channel we would need rectangular boxes, so we'll click on the icon representing a box. We see a box created under geometry elements along with the settings tabs open with the default values. We'll modify this according to our requirement. We'll give it a name as box 1. We will change the center point of this box and also the size of this box. When we click on apply, we can preview the box with the updated values in the settings. We confirm these settings by clicking on build until. This forms an inlet channel. For our model we require one additional rectangular box that follows this inlet channel. To create another box, we click on the plus icon and under geometries we select box. We modify the settings of this box. We give it name box 2 and a different center point and size. We click on apply to preview this. We see that this second rectangular box follows the inlet channel, and we confirm this by clicking on build until. If we look under the entities, we see that there are two volumes created, each corresponding to the two boxes we created earlier. We would like to combine these two volumes into one. We can do so by performing a Boolean operation. So we select union under the Boolean operation. Now to perform the operation we need to select the volumes on which this is performed. There are two ways of selecting the volumes for the operation. We can either select the volume directly from the display window or we can add them from the list. We confirm the selection by clicking on apply. Clicking on build until will now perform the union operation. We can see that under the entities we now have only one volume, which is the result of the union operation. If there are no more changes needed to be done in the modeling, we can confirm the model changes. This locks the model editing so that no accidental changes occur. This completes the modeling process, so we now move to the support tab. Here we can create materials and different regions and also shared expressions. We'll first start with materials. We select air to be our fluid medium. We click on confirm. This opens the settings tab and we should select a volume on which this air material properties would be applied. We click on the complete domain and click on apply. We can see the default properties of the air material such as density, dynamic viscosity and so on. It is possible to edit these values according to our requirements. For now, we will proceed with the default values. We would also like to create some outer regions on which boundary conditions would be applied. We'll first select a surface. We want to apply an inlet velocity constraint on this inlet surface region. So we give it an appropriate name as inlet. Similarly, we create a region for outlet where we would apply zero pressure, and we will group the top and bottom surfaces where no slip boundary conditions would be applied. The remaining surfaces are the side walls. We group both the left and right side walls into one, and on these surfaces a slip boundary conditions would be applied. We'll see in the next tab how to apply boundary condition. So we have all the regions that we require. Now we'll look at the shared expression. Shared expressions allows us to create expressions which can be used in applying boundary conditions or in scripting interface. For our case, we will create two shared expressions. One is called new minimum. This is the lower bound value for the kinematic viscosity, and it takes a value of 1 e power minus 6. Similarly, we create new max, which is the upper bound value for the kinematic viscosity, and its value is 0.5. Now we can move to the physics tab. We can add the physics by clicking on the plus icon. For the fluid flow, we select laminar flow physics. As stated earlier, we would like to perform a steady state analysis, so we keep the analysis type at steady state, and we select the volume on which we would like this physics to be valid. We also see the two fields that would be used in the laminar flow, which is the pressure and velocity field. After adding the physics, now we can proceed to adding interactions or boundary conditions. We click on this icon and we see that there are two interactions available, one for velocity and one for pressure. Let's start with the velocity. The first constraint is an inlet velocity. This is applied on the inlet region, so we select inlet. The inlet velocity given is 0.5 in x direction, and the y and z component of the velocity are 0. We now select the pressure constraint. The pressure constraint is applied on the outlet region. We select the outlet region as a target, and a 0 pressure is applied on this region. The third one is again the velocity constraint. We want to apply 0 velocity constraint on the top and bottom walls. This forms the no slip boundary condition. Since the walls are not moving, the constraint volume value corresponds to 0. The last boundary condition is the slip boundary condition on the side walls. For the slip boundary condition, the x and y velocity components are unconstrained, so we disable the box for x and y components, and the z components is set to 0. This ensures that there is no fluid flowing out of the side walls. This completes the application of boundary condition. We can now move to the simulations tab. Let's add a simulation. In the settings tab, we can provide an appropriate name. We see that the analysis type we had selected earlier is shown here, and also the laminar flow physics which was added. Under the concurrency, we can choose the number of nodes and the type of node depending on the computational resource required. We can now proceed to meshing the geometry. We can choose from one of these options. In order to get a reasonably good quality mesh, we can go to the expert settings. Under this, we can select default and provide a scaling factor. We will give it a value of 0.1 and click on apply to confirm these settings. We'll now start the meshing process. Once the meshing process is completed, it is indicated by the success status. We can preview the mesh by clicking on show preview. We'll now proceed to adding outputs which would be required in order to visualize the pressure and velocity fields after the completion of the simulation. We will select the pressure output. We want to visualize it on the complete air domain. We click on apply. We do similarly for the velocity field. We now have everything set up to perform a Newtonian fluid flow. But we would like to simulate a non-Newtonian fluid flow, and hence we want to modify the material model from Newtonian to non-Newtonian. To do so, we will use the flexibility offered by the scripting interface. We enable the scripting option and click on the script. We see that it has certain auto-generated script and also the main Python simulation script. These scripts in total encompasses all the settings we have so far performed in the graphical user interface. We can have a look at these regions where all the defined regions such as air, inlet, outlet, top, bottom walls and side walls are available. And under the expression, we can also see the minimum and the maximum viscosity values, or the lower and upper bound values which we had created earlier, are also available. And under the materials, we can see the different material properties of the air. We'll quickly go through the simulation script and see what it contains. So in the first block of code, we see that the mesh created is loaded, and in the second and third block of code, we see pressure and velocity fields. We also see the interpolation orders. So the default value is set to 2 for both pressure and velocity. However, we want to set the pressure interpolation order to 1 so that the LBB condition is satisfied, which ensures that there are no instability in the simulation. In the further blocks of code, we see the boundary conditions or the constraints that were applied, starting with the inlet velocity in the inlet region, then the pressure outlet in the outlet region, and no slip boundary condition in the top and bottom walls. Also the side walls which have a slip boundary condition. Then we can see the laminar flow physics that was added. This line of code returns a weak form of predefined Navier-Stokes equation. It contains both mass and momentum conservation equation. Then the .Allsolve function, when executed, performs a nonlinear Newton iteration to arrive at the solution. And for visualization, we see that the pressure and velocity output fields which were selected are written here. Now with this script, we would be able to run the simulation. However, this would be for a Newtonian fluid flow. The reason is, if we look at the arguments passed to the predefined Navier-Stokes equation, we see that it takes in a dynamic viscosity value. This parameter dot dynamic viscosity value is the default constant value of the air material. However, we would like to change this fluid property from Newtonian to non-Newtonian. We would see how to modify this material model in the script. Let's say the non-Newtonian material model is declared by the keyword mu. Now in a non-Newtonian fluid model, the viscosity is not constant and has a spatial distribution. One of the simplest and most widely used material model for non-Newtonian fluids is the power law model. So we would use the power law model to define our viscosity. According to this model, it states that the kinematic viscosity is K times power of strain rate to n minus 1. The K here represents flow consistency index and N represents flow behavior index, with N greater than equal to 0 meaning the fluid is shear thickening. We give a suitable value for these two index. Now we have to define the S. The S here is the magnitude of shear strain tensor, and this is given by square root of 2 times the double dot product of strain rate tensor. We are still left to define the strain rate tensor, which is given by the following formula. this returns the velocity gradient tensor. The second term is the transpose of the velocity gradient tensor. The kinematic viscosity value is at the moment unbounded and can result to some stability issues and non-convergence. So we improve on this by utilizing the bounded values which was defined in the expression. So we will limit our calculated viscosity values to be between nu minimum and nu max. We'll first do a lower bound of this value. To do so, we use if positive function which checks the condition and accordingly calculates a value for true condition and a false condition. So the expression that we want to check is expression dot nu minimum if this condition is true, then we bound the viscosity value to nu minimum, else we do not. We do the same for upper bounding. We use the same if positive function. Here we check whether our updated viscosity value is greater than nu max. If it is, then we limit it to nu max, else we retain the previous value. This should be expression dot nu max. Now we will define the dynamic viscosity, which is nothing but the density multiplied by kinematic viscosity. Now our predefined Navier-Stokes function would take the viscosity that is defined according to the power law model. We still have to make some minor modifications to our Navier-Stokes function, especially the Boolean flags that are set. So the first Boolean flag is include time derivatives. We are performing a steady state analysis, so we do not need to include the time derivatives. Hence this is set to false. The second flag is called ease density constant. This is set to true as we have assumed that the fluid flow is incompressible. The third Boolean flag is called as is viscosity constant, and since we are considering a non-Newtonian fluid which is a function of strain rate, therefore it won't be a constant anymore. This has a spatial distribution, and hence the ease viscosity constant flag is set to false. With this modifications, we have now converted the script to consider non-Newtonian fluid instead of the Newtonian fluid model. Now we are ready to run the simulation, so we proceed to the simulation tab. Now we can start the simulation by clicking on Run Simulation button. Once the simulation is completed, we can see the status change to success. We can also view the logs from under here. Now let's visualize the output fields. We will add the first visualization for pressure. Then we can add a second visualization for the velocity field. This completes the simulation demo for non-Newtonian fluid flow. See you in another demo video.